Today we are going to talk about near field cosmology with metal poor stars. This topic is also called stellar archaeology. So, there is a notion that cosmology is a study of objects which are at very large distances. However, objects which are close by in our backyard, like Milky Way stars and our satellite galaxies around Milky Way, they provide valuable constraints to some of the cosmological problems, like the first stars which are formed in the universe and what is the nature of them. And these studies need to wait until the future facilities which are going to come for detection of these first stars.
So before we start the lecture series, I would like to introduce few terminologies. One is metallicity. Metallicity in astronomy broadly refers to chemical abundances of all elements that are synthesized beyond the Big Bang nucleosynthesis. These heavy elements are made inside stars, and most often metallicity in stars are measured based on the abundances of iron. So this is primarily due to the fact that there are plenty of atomic transitions due to iron present across the wavelength range, like from UV to infrared wavelengths, you would see plenty of transitions due to iron. In the case of interstellar gas, the metallicity is measured based on abundances of oxygen, and the fact that in the case of interstellar medium, heavy elements like iron would be locked up into dust grains. So gas phase abundance is what is used as proxy for metallicity. Both iron and oxygen are one of the most abundant element that are synthesized a lot in the supernovae nucleosynthesis. And the next one, by definition, the square bracket Fe by H is defined as a logarithm of number density of iron over number density of hydrogen inside a star minus logarithm of iron over number density of hydrogen in sun. So the square bracket equal to 0 refers to the solar metallicity. So that means the relative ratio of iron over hydrogen is same as that of the sun. In terms of mass fraction, this is equivalent to 2% of heavy elements, that is Z equal to 0.02. So as you can see in the case of old stars like the old Milky Way halo stars and globular clusters, you would see the metallicity is negative. So they have lower, like if -1 refers to 10 times metal poor than the sun. In the case of top 3 stars or the first stars, the notation Fe by H is not quite relevant. So primarily we use Z equal to 0.0. That refers to the mass fraction for a pop 3 star. So pop 3 stars are also always referred as zero metallicity stars. So Fe by H 0 refers to solar metallicity, and Z equal to 0.0 refers to zero metallicity pop 3 star or the first stars. And in this current slide, I would like to introduce the evolution of low and intermediate mass stars. This you might have already learned during the first module. And this evolutionary track shows evolution sequence of a star from 1 to 8 solar masses. So these stars evolve 2 times into giant branch phase. So first time after they exhaust hydrogen in their core, they start to burn hydrogen in the shell, and these during the shell burning, they ascend towards giant branch. This is called RGB or the red giant branch phase. During this phase, they burn hydrogen through CN cycle, and this is the first time the surface composition of a star start to change from the primordial star-forming cloud from where it is born. So first time the star is enriched with the CN burning product, CN cycle product. So that is nitrogen is enhanced and carbon is depleted in the case of a red giant branch phase star. And further, the star start to burn helium in the core. This is the second main sequence, or a red clump star. So further again, they climb, ascend towards giant branch second time. So this phase is called the asymptotic giant branch. During this phase, they alternatively burn hydrogen and helium in their shell. So there is a rich nucleosynthesis which happen in this intershell region between the hydrogen and helium shell burning. So as you would see in the further lectures, this is where the slow neutron capture actually happens in the case of asymptotic giant branch phase.
So there are about 3 lectures to cover this topic. So the first lecture is going to have some outline of the stellar nucleosynthesis, which will be used as a probe for chemical evolution and the chemical history of the early universe as well as the early galaxy, and different time scales at which the elements are produced in the universe. In the next lecture, we talk about various chemical abundances which we observe in these very old metal poor stars. And they also give constraints on the sites of nucleosynthesis. And they also say the galaxy history, how the chemical evolution and star formation history of the galaxies in the early epochs. And in the lecture 3, we talk about the first stars. How do we derive constraints based on these extremely metal poor stars? And we outline the theoretical and observational perspective and time when and where these first stars form, and what are the constraints we derive from the low mass extremely metal poor stars in probing the nature of the first objects which formed in the universe. The formation of first low mass stars can also be probed with these stellar archaeology, and at the end we talk about some spectroscopic surveys which are useful in understanding these subject. So let's start from the beginning. So everything started with the Big Bang, and following the Big Bang, the universe expanded and protons and neutrons formed, and they combined together to form hydrogen, and from hydrogen many other elements were synthesized. So this epoch is called the Big Bang nucleosynthesis, and it's about 3 minutes after the Big Bang. The primary nuclei which were produced during this time is hydrogen, helium, deuterium and lithium. And further the universe expands and cools, and once we have the hydrogen molecule formation happens, the first stars form and make the first heavy elements in the universe. So the stellar nucleosynthesis process are the main responsible for all the heavy elements beyond lithium which are observed in the universe. And this is the outline of the Big Bang nucleosynthesis, and this is the schematic layout of the various nuclear reactions, and primarily deuterium, helium and lithium were produced, and this is the ratio at which, the fraction at which they are made. And so for every 12 hydrogen atom, 1 helium atom is made, and this is coming from the freeze out of neutron to proton ratio at a value of 6. And lithium is very minimal, kind of a very trace amount, about 10 power minus 10 with respect to hydrogen is made. And there are no other elements beyond lithium is produced in Big Bang, and it's primarily due to no stable nuclei at the mass number 5 and 8. And further the universe expands and the densities and temperatures become low. So 3 body nuclear reactions were not possible at low density, so triple alpha process didn't really happen, which happened very effectively in stellar interiors, and carbon is synthesized by combining 3 alpha particles. And this is the observational evidence of deuterium and lithium in the universe. And this, the plot on the right shows the intergalactic medium detection of deuterium. This is from the quasar absorption line of the intergalactic medium. And you can see the red band shows the model predictions, and these observed points which are shown in blue, they match quite well with observations. And on the left, we see the lithium doublet, which is observed in the metal poor stars. And you can see at various metallicities, this line is detected. And these are the comparison of observations with the theory. The observed helium, deuterium matches reasonably well with the Big Bang prediction, whereas the lithium abundance is way off from the expected theoretical predictions. And this is again further highlighting the cosmological lithium problem. So here on the left, what you see is lithium abundances from metal poor stars. So they range a variety of metallicities from -5 to -2, and this plot also shows there is no systematic differences, systematic effect due to the temperatures of the stars, and one can see a nice plateau of lithium abundances, and this plateau is called the speed plateau, and this indicates the lithium origin in metal poor stars are primordial in nature. And you can also see that there are no stars which are seen above this lithium plateau, and the Big Bang nucleosynthesis prediction is 3 times more than the observed lithium value. So this is called the cosmological lithium problem, which is still an open problem and we don't really understand it well. And the possible sources of this problem could be, the discrepancies could be, depletion of lithium by very massive first stars. And if the massive stars deplete lithium in their interiors, that could reduce the primordial values. However, these massive stars which also produces heavier elements. So this lithium depletion and the production of heavy elements are not found to be consistent. So this is not one of the viable scenario, but this could have some effect. And another possible sources of lithium depletion is stellar diffusion. And this is studied using a globular cluster. The plot is shown in the right. So a sample of stars which are chosen on the main sequence as well as on the subgiant branch, and the diffusion due to the long-lived main sequence stars, the lithium is gravitationally settled compared to hydrogen, and whereas on the subgiants, due to some amount of convection, diffusion is not very efficient. So the differences between lithium abundances between these main sequence stars and subgiants that can be seen here, and this is also thought to be one possible reasons for reduced lithium what is observed in the main sequence stars. But this problem can be addressed better by observing many more globular clusters and stars which are on the main sequence of globular clusters, because giant stars deplete lithium due to convection. So we have to observe stars which are on the main sequence. And other possible way to look into the problem is observing lithium on the main sequence in the external galaxies and lithium in the intergalactic medium. So these are the possible sites where we can study the lithium abundances and see whether still lithium problem persists or not. And this is currently not possible until we have the next generation of telescopes coming online. So we have seen in this plot the temperatures of the stars which were considered in the study range from 5,800 to 6,500. There are no cool stars. Here the next step we want to talk about the cosmic abundances of chemical elements. So this is a periodic table for astronomers. You can see hydrogen occupies a major fraction, 75% in terms of mass, and helium is the next dominant element, and all the other elements which are shown here, there are little boxes. So that shows the approximate relative abundances of these elements with respect to hydrogen. So majority of the elements, chemical elements which as we see is hydrogen, helium, and heavy elements are very trace amount. But these are very important for probing the chemical history of the universe. And this plot shows the solar system abundances with respect to silicon, and how do we get into such rich variety of chemical elements ranging from hydrogen to the most neutron rich, heaviest uranium and thorium, and how are they made in stars. And so these different peaks kind of indicates various nuclear processes which happens in the stars. So carbon is produced in AGB stars. Carbon is also produced in massive stars, but they burn further into making oxygen. And alpha process produces all the alpha rich nuclei like oxygen, magnesium, silicon, sulfur, and so on. And this is the peak where you have the iron peak elements. So these are produced by supernovae, both type 2 and type 1 supernovae. And beyond iron, nuclear fusions don't produce these elements. So they are made by neutron capture and proton capture processes. And you can see various peaks indicating R process and S process peak, where these elements are showing the magic number of the nuclei. The cosmic ray spallation event, in which cosmic rays hit carbon and nitrogen and oxygen nuclei and produce these lighter elements like lithium, beryllium, boron, and some of the lighter elements are also produced during the supernovae and novae mechanisms. And lithium primarily is produced by Big Bang, but stellar nucleosynthesis processes in lithium rich K giants and AGB stars also produce lithium by a mechanism called Cameron and Fowler mechanism. And this plot shows the evolution of lithium and beryllium at different metallicities. As you can see, the lithium abundance is a plateau at low metallicities. At higher metallicities, the stellar processes like RGB production, AGB production, and cosmic ray spallation events make lithium, and that further increases the lithium abundances in the ISM. In the case of beryllium, you can see a linear increase in the beryllium abundances with respect to iron. So that clearly indicates it's not primordial in origin. Beryllium is produced due to a spallation process which increases with metallicity, and the linear increase kind of indicates the seed nuclei at which the cosmic ray hits, and the cosmic ray itself, both are produced by the same event. So that indicates the possible sites could be novae and other processes. Okay, we switch gears and go to origin of all the heavier elements which are observed in the solar system. And this is a nice periodic table which shows various processes which makes these elements, and also the shaded colors indicate various fraction which of different processes which make a single nuclei. And so the most of the helium in the universe is made by Big Bang nucleosynthesis. First time elements beyond lithium is synthesized in stellar interiors. And stellar interiors, the bottleneck of beryllium and boron nuclei was bypassed due to the higher densities through triple alpha processes, and that forms carbon. And further alpha capture of carbon produces all these other elements like oxygen, neon, magnesium, and so on. So for a detailed review of this, the seminal work by B square FH, it clearly explains all the various processes. But there are a lot which has happened from then, and which we would be talking about in the next few slides. So these are the various advanced nucleosynthesis processes which happens in the advanced stages of nucleosynthesis processes in the massive stars. So hydrogen burning and helium burning and carbon and neon, oxygen and silicon burning. So you can see the main products and the byproducts. These are also very important. They produces the intermediate nuclei, which are odd nuclei, which are not produced in the alpha-rich processes. And we can also see the various time scales for 20 solar mass stars. And here the table shows the contrast between a 20 solar mass and a 200 solar mass star, which the time scale, which are quite different for various nucleosynthesis processes. So massive star, as the stars become more massive, the hydrostatic burning happens for a very short time. So silicon doesn't burn completely, and incomplete burning silicon normally ends up as an alpha rich freeze out during the explosion, and that avoids free neutrons, and which would have helped in making neutron capture elements. And this is again a structure, onion shell structure, which shows how the elements are made, and this clearly indicates the various nuclear processes which happen. The structure itself clearly illustrates. And the plot or the figure on the left shows the sizes. So the very center you have the core, we have the iron core, and the other layers follow them, and you can see the different sizes here clearly. And during the explosive nucleosynthesis, the rapid neutron capture elements are produced. This is primarily made by not very massive supernovae. Primarily by supernovae are thought to be primarily by supernovae of 20, 15 solar masses. And the silicon burning makes nickel, and nickel further radiatively decays into all the ion group elements. And explosive burning of oxygen and neon also produces various odd nuclei like sodium, aluminum, phosphorus, and so on. These processes also make some amount of boron and fluorine. And this is a good plot which shows various masses of stars, what is the fraction of elements it makes. So you can see they are very sensitive to the mass, initial mass. And massive stars, the takeaway from here is massive stars do not spend a lot of time in the hydrostatic burning, and it ends up as a alpha rich freeze out, and neutron capture reactions does not happen in these massive stars. And due to incomplete silicon burning, the massive stars produce a lot of lighter alpha process elements compared to the heavier ones. And supernovae are also thought to be a viable site for neutron capture, rapid neutron capture process. The possible sites are supernovae, and supernovae jets and merging neutron stars. So the necessary condition for our process is the high neutron density and high entropy. So the nuclei, what you find, like all the R process nuclei is far from this valley of stability, because the beta decay time scales are much larger than the neutron capture time scales. Elements which are far from the stability is created. And neutron star mergers are an interesting site for making our process, including the heaviest neutron-rich nuclei like uranium and thorium. And they produce all the neutron-rich elements in the universe. Though there are current thinking that supernovae also contribute to our process, but the lighter our process elements like europium and below. And this is a pair instability supernovae. They are thought to be predominant during the early stages when the stars are metal poor and stars are more massive, and these massive stars end up as a pair instability supernovae. So the initial masses are about 150 solar masses, and they don't leave any remnant. The entire star explodes. That means it makes a huge amount of heavy elements, and they enrich the universe with rich heavy elements, and the metallicity of the universe increases quite fast. And they also have a very typical abundance pattern, the odd even effect. So you can see in this plot, all the alpha rich even nuclei are enhanced and the odd nuclei are underabundant, and they produce low nitrogen to oxygen ratio. So this is also something quite important in the terms of primary nitrogen production, which are seen in the IgM. And they don't produce any elements beyond zinc and no R process elements, because they end up as alpha rich freeze out during the explosion. And this is a pretty pictures of the supernovae remnants, and not going into the details. So the emission, gamma ray emission from these remnants also provide valuable clues of the nucleosynthesis which happens inside this pre-supernovae and supernovae processes. And type 1a supernovae, they are formed in a binary system. So a normal binary star, and one of the massive one among them becomes a giant and transfer mass to the companion, and the star becomes a white dwarf, and the binary companion, when it goes through a red giant phase, it accretes matter onto the white dwarf, and which when it exceeds the Chandrasekhar limit, mass limit, it explodes as a supernovae. So this supernovae also does not leave any remnant, and the entire mass explodes with rich processed heavy elements, primarily iron peak elements. So type 1a supernovae produces about 2/3 of the iron which is seen in the universe. And the AGB nucleosynthesis, stars which are of masses between 1 to 8 solar masses, they all go through asymptotic giant branch phase, where you have a carbon oxygen core and helium and hydrogen burns in the shell, and there are rich nucleosynthesis process which happens in the intershell region. So there are complex process which makes slow neutron capture, and they produce lot of nitrogen and carbon during this mixing process. And so this is the plot shows which the yield of carbon and nitrogen for various initial masses of the star. And this is an illustration to show how this mixing is very important in making some of these intermediate nuclei. So slow neutron capture in AGBs happen along the value of stability. So every neutron capture is followed by a beta decay. So elements are synthesized one step at a time. So this is the recap of all the nucleosynthesis sites which we talked, and also the time scale. So light elements are produced during Big Bang, and the massive stars produce all the elements from carbon to neutron capture, both during the hydrostatic burning and during the explosive burning. And this is typically less than 10 power 8 years. And for AGB stars from 0.8 to 10 solar masses, they make all these carbon to fluorine and the S process elements about 10 power 9 years. And type 1a supernovae, they make copious amount of iron between 1.5 to 2 into 10 power 9 years. And beryllium and boron is made during the cosmic ray spallation. And odd nuclei like sodium, aluminum, and phosphorus, they are created during these hot hydrogen burning processes in massive stars. In summary, first time stars produce the first heavy elements in the universe, and they have different time scales of this element production, and that helps the abundance ratios kind of help chemically tagging the star and understand the chemical history of galaxies.